Okay, so we are continuing with this Maxwell's correction to Ampere's law. So let me state once more what the problem in here is, right? So let me do it like this. So this is Ampere's law. So around any Amperian loop, the line integral of the magnetic field, that's equal to mu0 times I enclosed, the current enclosed. So we just consider this Amperian loop in here. And for the current enclosed, we basically have to think about current that crosses some kind of a surface in which this Amperian loop is the boundary. I can choose the surface like that, in which case the current is definitely I. But if I choose the surface like this, it's the surface passing between these two, between the place of this capacitor, in which case the current is equal to 0, right? So for all other surfaces, it looks like the enclosed current gives us the same value for the right-hand side. But somehow for some particular surfaces, for this surface, we have somehow, since the current in here is equal to 0, there's some kind of an inconsistency in here, okay? And then Maxwell said that, well, in that case, he said that, let's just correct this. So, well, this is not true, therefore, what we have to do is to add some additional term on the right-hand side. So, it's again, the line integral of the magnetic field. On the right-hand side, however, we have the real currents plus something called the displacement current. Okay, so I is the real current, right? That's there. It should be there. And then he just invented something and called it as the displacement current. Well, there's no such current. It's just a let me write displacement current in here. So it's just a quantity that has the dimensions of the current, but it's computed in terms of some other physical quantities, okay? As a result, we are just going to give the definition in a moment, but he said that, well, somehow it is possible that there are places where this is equal to 0. There are places where this is also equal to 0, but somehow they should add up to the same value independent of what the enclosed surface is, all right? So that's basically what we are requiring from that displacement current expression. So as a result, let's say it like this. The displacement current, for example, in this part of the wire should be equal to 0. In this region, somehow there should be some kind of a displacement current that should be equal to the value of the real current on the wire, okay? And here the displacement current should still be, again, equal to 0. So as a result, the total is always equal to I, right? So let me also write total in here. Okay. So that's basically what he was thinking, right? Okay, so in any case, so as a result, we have to somehow come up with this displacement current expression, and we have to write it in terms of some kind of a physical variable. And this is what we notice in here. Because the current is flowing in here, the charge on the plates are increasing. So let's say it like this. Yeah, I'm just going to write this thing down in a moment. In any case, because of that, right, because of that, I think I'm going to use red color to distinguish it from the other things. There's an electric field between the plates. Okay, there's an electric field. And this electric field is changing with time, right? We can really write down the expressions in here, but I'm just going to try to express it like this. So yeah, let me quickly go through this. Why the current is related to the charge? Because I know that the current is the rate of change of this charge on the plate, right? That's how the current somehow enters into the picture, and somehow the expression, yeah, right. That's the first thing that we should keep in mind. And then there's an electric field in here. So what's the electric field magnitude between the plates? I'm just going to assume that this is a parallel plate capacitor. Let's say that A is the area and D is the separation. Okay. So in any case, this is basically, if you remember, sigma divided by epsilon 0. The things do not change a lot if I place a dielectric, right? So don't worry about these kind of things. But let's just see this version in here. What is sigma? It's basically charge divided by the area. Okay. In any case, if you then write this thing down, so the charge is therefore can be written as epsilon 0 times area multiplied with the electric field. And what I would like to do is basically just take the time derivative of that expression, in which case this is related to the time derivative of the electric field, right? That's how somehow, I mean, we can easily see that the time derivative of the electric field is directly related to the current flowing into the capacitor. So as a result, if I want to write down an expression for the displacement current for that region, I need to use this expression in here. So as a result, let's say it like this. This is the displacement current expression. So let me just write it down like that. This is defined as, let me put it back like this. This is, sometimes we use these three equality lines, equivalence sign to express that a quantity is defined like that. So we just define the displacement current as epsilon 0 times A times the time derivative of the electric field. Okay. Why is this a current? Well, it is not. Okay, I mean, let's just repeat this. Maxwell calls it as a displacement current because it has the dimensions of the current, right? Otherwise, it has no physical meaning as a current. So don't get confused by this. It's not a current. Why does he call displacement? I don't know. I mean, he was basically thinking about something else, some kind of an, I don't know, metaphor or something like that. I'm not really sure what that name actually implies. For us, the name is, I mean, the reasoning behind this given name is unimportant. That's irrelevant. Some people just call this as displacement current. And as a result, all of the people after that actually keep using that term. And I'm using that term for that reason, not because it has some kind of a meaning, okay? So in any case, let me just, I'm just going to summarize it at the end. I mean, the name could have been anything. It could have been a meaningless new word, right? Something like XYZ, for example. But people usually choose words for terms from some existing words, usually, because they use some kind of metaphors and things like that. And there is the same thing that has happened in here. But whatever, right? Whenever you see a displacement current expression, displacement current term, you have to understand this kind of an expression. Okay. There's some kind of confusing things in here. There's some kind of epsilon 0 and an area in here multiplied with this. But let's just correct this first of all. So area multiplied with the electric field is basically the electric flux. And so as a result, we just correct this. So we can then talk about the flux that crosses this enclosed surface. So let me just write this thing down, right? So this is the enclosed surface. The surface that's enclosed, so that's the boundary of the surface. All right, let's just put it like that, okay? let's see, sorry. Yes, there's an electric field in here. And, yeah, that was supposed to be blue, sorry. So the Amperian loop was supposed to be blue. All right. In any case, on that surface, part of that surface, there's an electric field which is going out. In this case, it is uniform, but it didn't have to be uniform. There might be situations where the surface might be curved and might be making an angle and things like that, right? So we basically define the flux, sorry, that, sorry, electric flux that crosses the enclosed surface. In the direction pointed by the surface normal. Let me add this, right? It's just the electric flux. So I'm going to use the capital phi letter for this. But this is the flux of the electric field now. It's the integral of the electric field dotted with the area. Okay, so first, this is an open surface, right? It's a surface with a boundary. It's not a Gaussian surface. And so as a result, I don't put an O sign in here. So that's not a load, all right? Just keep this in mind. So that's an integral over an open surface. So this is just a reminder. Just keep this in mind, right? So that's the first thing. The second thing is, all right, there's actually some kind of a vector involved in here because you're talking about some kind of an area element, right? The area, if you remember, is a vector which is perpendicular to the surface. So therefore, it has a direction, and let's just remember that, at least for open surfaces, there's an ambiguity in the direction of the surface normal. I'm sorry. So I need to define this area vector as the real surface area is a scalar multiplied with the surface normal, but I can choose the surface normal in two different ways. I can choose it like that or like the other way around, right? But in that case, this n has to be consistent with this direction on the Amperian loop in here. So let's remember this. So there's a direction on the Amperian loop, here on Amperian loop, right? And there is a direction on the surface normal. So here there is a surface normal in here. So let me also write this thing down. So the direction of the surface normal. Okay, we have mentioned this. They have to be consistent with the right-hand rule, right? So that's what we are requiring. So, I mean, these are two different directions of two different things. One is a direction on a curve. The other one is a direction of a surface normal, right? Let's say it like this, must be consistent with the right-hand rule. Right-hand rule, right? Let's just remember this. So we need to, this is another place where we need to insist on the choice of the directions, all right? So the directions have to be consistent. Just like the enclosed current is computed in the same way. It's the current flowing along the direction of the surface normal. This is also like that, right? So therefore, this is an electric flux crossing an open surface. For the case of this capacitor, it is the electric field is uniform over an area A. So therefore, we get this expression. So therefore, let's say it like this. So phi E is equal to A times E for the capacitor example. Okay. So in any case, so that's the one that we have been using in here. So therefore, this is the rate of the change of the electric flux, actually. So I mean, this is basically how people write down. So let's say it like this. This is the displacement current crossing the enclosed surface. This is defined as epsilon zero multiplied with the rate of change of the electric flux, the time derivative of the electric flux. Okay, so as a result, we get this new law in here. So it's called the Ampere-Maxwell law. It's not just Ampere's law anymore because Maxwell has made a correction. So because of that, it's called the Ampere-Maxwell law, right? Right. So it is of this form. I'm just going to write down the integrals in here. Just forget about the other details and the curves and things like that. So this is true in general. So we have mu zero times, the line integral of the magnetic field is mu zero times the enclosed current that crosses that surface plus epsilon zero times the flux, that the electric flux that crosses the enclosed surface is time derivative. Okay, so both the current in here and the flux in here are basically the things that are crossing that enclosed surface. So yeah, let me draw the picture again. So we have an Amperian loop all the time, right? Let me draw it like that. So that's the Amperian loop. So on the left-hand side, the loop enters into the picture. And then we have an enclosed surface, might be any shape, but this is really a surface. And so therefore it has a surface normal in here, consistent with the direction on the Amperian loop. And to compute the enclosed current, we compute the current that crosses that surface. So let me kind of show it like that. So the enclosed current is the current that crosses that surface. Plus there's this electric field that crosses the surface. So that will basically give us the enclosed flux in here. You can think of it as the enclosed flux. And so as a result, the time derivative of this flux and the current in here somehow contributes to the magnetic field. All right, let me box this like that. Yeah, I'm just going to box it like this. Okay, so I'm just going to solve one example, and that's the only example that I can solve because this is already complicated. Yeah, I cannot solve better examples. That's the problem in here. And I mean, otherwise the problems will get complicated. So there's only one problem that I can solve. That's basically a parallel plate capacitor with disc-shaped plates. All right. So I'm going to explain why this problem is the one that we can solve. Because it has some kind of cylindrical symmetry, actually. It has a symmetry, so that enables us to solve that problem. In any case, but let's first talk about this equation in here. So basically what Ampere said, without this part in here, right? What Ampere has said, that the electric currents produce a magnetic field. Now, Maxwell is saying that, well, it's not just the electric currents, but a time-dependent electric field also produces a magnetic field, right? So that's the important conclusion in here. So if you remember, this is just the complementing part of the Faraday's law. So let's say it like this. So basically, this is what Maxwell says. Let's say if the E field changes with time, then a magnetic field is produced. Okay, that's basically what that equation tells us. So there are two different ways of producing a magnetic field. You basically use an electric current, an electric current produces a magnetic field, or you produce some kind of an electric field and you just change it with time. How can you do that? Well, I mean, to change the electric field with time, you have to move charges somehow. So there has to be somehow some kind of charges moving. In that way, an electric field would be changing, right? So there's always some kind of a charge motion that should be happening in that case too. But in any case, I mean, somehow, if you make sure that the electric field changes with time, you produce a magnetic field. So let's remember this. This is the Faraday's law. So, yeah, that's what Faraday was saying is that if the magnetic field changes with time, right? That was one of the implications of the Faraday's law. If the magnetic field changes with time, then an electric field is produced. We have discussed why this should be the case. If you remember, we have used some kind of relativity principle as well, but whatever, somehow we have deduced that this must be so. Somehow a magnetic field should, a time-dependent magnetic field should produce an electric field. Now, Maxwell says the opposite. If the electric field somehow changes, then the magnetic field should be produced. Okay, so this is the key observation, actually. This kind of says that if you change one of the fields, then the other one is produced. But that other one is also time dependent. So that would mean that it would also produce the other field and so on. So as a result, there's this kind of a chain of events in here. So somehow you can, I mean, by using this kind of a thing, this kind of a, I don't know, mechanism, you can explain the electromagnetic waves, actually, more or less. And this is what I'm going to say, actually. Okay, so I think this is the first thing. Okay, but let's just first talk about this, okay? I'm just going to solve a problem and then I'm going to talk about the implications later. So I think this is the last problem that I'm going to solve. All right, I'm exaggerating in here. I'm just, this is a parallel plate capacitor. All right, there's a current flowing in here. So it has a radius R. I'm just going to use capital R. I don't have anything with resistances and things like that. So as a result, I'm just going to keep using this capital R symbol. No problem with this. So let's say it like this. Parallel plate capacitor has disc-shaped plates with radii R. Okay, so there's a separation in here. So it looks like the separation is too large. Well, this is basically the defect of my drawing. I mean, in reality, they have to be very close. I'm actually using the assumptions that we have made earlier. The separation between the plates should be so small compared to these lateral dimensions, the other dimensions, so that I can make this infinite plane assumption. So that's necessary, right? So I'm going to make this as a statement in here. Yeah, I'm just going to write this thing down, right? So that separation should actually be much less than R, right? So we still have this parallel plate approximation valid, right? Okay, so we have a point in here between the plates, let's say, which is at a distance little r from the central axis in here, right? So let's say it like this. Consider a point between the plates with a distance r from the symmetry axis. There's a cylindrical symmetry in here, and we talk about that distance in here. So find the magnetic field in there. At this point. Okay, so let's just analyze the situation. So we know that, for example, the magnetic field at a distance r from the wire, right? I think I'm using this purple color in here. So there's this right-hand rule in here. So this magnetic field is along this direction. This is a three-dimensional picture with a magnitude given by mu0 I over 2 pi r. Right? I'm just curious about the value of the magnetic field inside the thing between the, I mean, in the region between the plates. So what's the magnetic field at that point? Okay. So here there are no currents in this region, but there is a displacement current because the electric field is changing with time. Right? That's the idea that we are going to use. Okay. So let me draw the side view in here. So that might be, I don't know. Let me make this a little bit smaller. So this is the side view of the same picture. Okay. Again, I'm exaggerating. So these are the plates. Okay. And then I have a point somewhere in here, which is at a distance little r from the symmetry axis. And I'm asking for the value of the magnetic field at that point. Okay. I have just written down the value of the magnetic field at this point outside. So this magnetic field is pointing towards us. So let me draw the direction of the current as well. Right. So I have said that the outside the magnetic field has this expression mu0 I over 2 pi r. But I'm really interested in the magnetic field within that region. Okay. So it's quite easy to see that the magnetic field lines are still circles in here too, because of this. I mean, we can use the same kind of arguments that we have used before. So we can then do this calculation. I think I just need to add that I'm going to look at these two situations where this point is really between the plates, and sometimes I'm going to consider points which are a little bit outside between the plates, right? In any case, since this is easier to draw, I'm going to use this picture. Okay, let me magnify it a little bit and then go down. Okay, yeah, I think I'm going to draw this picture again with a white color. All right. Yeah, let me kind of draw it like that. Right? This is the side view, but I'm going to draw it, yeah. Forget about this. Okay, so let me draw the radius of the disks. So these are disks really. These are the currents. So the current is also given. Sorry about this. Yeah, I should really say that the current is I, all right? But within the statement, I didn't say this. Yeah, I mean, this is one of the givens. Without the value of the current, I cannot find anything. So in any case, there is this point in here, R, at a distance R from the wire. And I just choose an Amperian loop, right, as the shape of, in the shape of a circle, right? Let's just draw it like that, right? There's this axis passing like this. Okay, I think I made a mistake in here, drawing mistake, so I'm still using this, not the perfect side view, but it's the view where these plates somehow look like ellipses. So let me try to draw them like that, right? Okay, something like this. So that this Amperian loop also looks like an ellipse. So the Amperian loop is basically a circle parallel to those plates, and it is coaxial with the axis of symmetry in here. Okay, so then that's what we do. So the draw an Amperian loop. That passes from the point in question. Okay, so the loop is a circle with radius r. Obviously, it is coaxial with the symmetry axis of the problem. So there's this cylindrical symmetry in here, right? So it is this thing in here. So in any case, so there's a magnetic field in here. Let's just call this magnitude as B. So this is kind of pointing towards us actually, but in any case, we know that it's parallel to the surface, parallel to the Amperian loop. I think I'm going to draw this side, this view as well. So it's the view that you see when you actually look at it from that side. So let me also draw it like this. In that case, the plates will actually look like that. The current is coming towards us in the wires, and my point is in somewhere in here at a distance r. The magnetic field at that point is directed like this, and my Amperian loop is a circle like that. All right. So on that circle, the magnetic field is always tangent to the Amperian loop. It has the same magnitude everywhere, and it's always tangent and whatever. So as a result, I can easily compute this line integral of the magnetic field. I'm not going to spend any time on this. So I'm just going to write this thing down. So that's the Ampere Maxwell law. Sorry, this is epsilon 0 d phi e over dt. All right, let's just compute starting from the left. So we have d times 2 pi r for the line integral of the magnetic field. This is always the same. On the right-hand side, the current is 0. There is no current flowing from, the enclosed current is 0 because no current is flowing from through that circle in here. Okay, but there is an electric flux in here, so there's an electric field that's passing. So we can compute this electric flux in here. So the electric flux is crossing that part of the surface. If you want on this figure, it's the electric flux is passing from this surface in here. So let's quickly compute what the electric flux is. So electric flux is basically the electric field multiplied with the area of that enclosed surface. So that's pi r squared. I mean, we have done similar calculations, like, I don't know, in the case of this induction problems. We are basically computing the flux of a field, but this time it's not the flux of the magnetic field through a surface, it's the flux of the electric field, right? This is the analog of the Faraday's law, essentially. So the electric flux passing through that surface, right? It is given by the sigma divided by epsilon zero gives us the magnitude of the electric field, and sigma is basically the charge on the place divided by the area. What's the area? Sorry, this is Q divided by epsilon zero. The area of the place is basically, it had radius capital R, so therefore it is pi r squared. Okay, so in any case, so therefore epsilon zero times the electric flux is equal to Q times R squared divided by R squared, and Q in here is the total charge on plates, on positive plate. On one of the plates, right? Sorry. So if I take the time derivative of this thing, so that's the what we would call as the displacement current, that's equal to the time rate of the rate of change of the charge on the plate, but that's equal to the current. Okay, so as a result, I'm just going to insert this in here, right? So therefore, this is equal to I times R squared divided by R squared. Just as we have said, this is a quantity with the dimension of the current, but it's not really a current in here. It's basically the rate of change of the electric flux multiplied with some fundamental constant epsilon zero. All right, that's basically what it is. In that case, the magnetic field can be written as, let's see, mu zero I over 2 pi little r divided by r squared, right? Yeah, that's the expression. But I'm just going to add this up if r is less than r. All right, that's the exercise. Okay. Now I'm going to do it this time for a point outside. Right? If the point is outside, so that means r is bigger than r. So it's the same picture again. But this time the point is somewhere in here. And this distance is r. So if I look at this picture from, let's say from this point of view, then I'm going to see this. So these are the plates. Both plates actually appear as one. This is the radius of the plates, so this is the radius. I have a point outside. There's this point outside. What else? There's a magnetic field in here. It's this magnetic field. This is going to look like, the magnetic field is going to look like this as in this picture. I use an Amperian loop like that. It was a blue curve, sorry. The Amperian loop is a circle with radius little r. So in that case, the Amperian loop is going to look like this. Okay. What else? There is an electric field in here, but the electric flux is between the plates. So that means there are these electric fields in here. This time the electric flux is between the plates. So that's the electric field, right? So let's just remember that the field is zero outside. The field is, all right, this was just an approximation, but I mean, it's actually a valid approximation. So the electric field is zero just outside the plates. It is only between the plates, right? So there's only a certain region in here where there's an electric flux. Okay. So I'm going to do the same thing again. So it's the Ampere-Maxwell law. So it's the line integral of the magnetic field. On the right-hand side, I have enclosed current plus the time derivative of the electric flux. Right, that's the term. The left-hand side is line integral of the magnetic field is again the same in terms of the unknown magnetic field. On the right-hand side, the enclosed current is equal to 0. The real current is 0. I need to take the time derivative of the electric flux in here. So I write out the electric flux. So that's basically area multiplied with the electric field. So that's the full area. Full area of the plates only. So this is that area only. It's the area of the plates now. It's not the area of the Amperian loop. And what's the electric field in here? Is the sigma divided by the area. Sorry about the sigma divided by epsilon 0. What is sigma? Sigma is charge divided by the area. Well, what's the area? It's pi r squared again. So the areas cancel in here, so we get Q divided by epsilon 0 in here. So that's the electric flux. So the rate of change of the electric flux is, therefore, is 1 over epsilon 0 times the electric current. If I multiply with epsilon 0, then I get I in here. So in that case, the total displacement current is equal to the value of the current on the wire. Just as we have expected, because somehow Maxwell adjusted this expression in such a way that the total value of that thing is equal to the current, right? Indicates that this somehow Amperian loop actually covers everything. All right, that's basically it. So therefore, the magnetic field is therefore mu 0 I over 2 pi r, just as we have expected in the outside. So let's say this is for r is bigger than r. All right, let's just summarize it. So the magnetic field is therefore, this is between the plates. So let's say it like this: magnetic field between the plates. So it has this expression in here, mu 0 I divided by 2 pi, little r divided by r squared for a point inside. And it is mu 0 I over 2 pi r for a point outside. Right? And then we draw this magnetic field as a function of the radial distance. It's the magnitude basically. So inside, between the plates, inside, within the capacitor, it increases linearly. It reaches to the maximum right at the edge of the capacitor. And then after that, it just has the usual 1 over r behavior. Right? So inside, it is proportional to r. Outside, it is proportional to 1 over r. All right. So what is interesting in here is this is it interesting? I think it should be expected, right? So, I mean, in this region, for example, for a point which is at a distance r from the wire, the magnetic field has this magnitude of mu 0 I over 2 pi r. Now, what we see is that if I just take the point somewhere in here, but this time this point is at a distance little r from the symmetry axis, but from a point between the plates, right? In that case, too, the magnetic field outside has the same value. The reasonable part in here is that if this little r is too large, in that case, this should be the expected result, because we don't care whether the capacitor is in here or not. It's not going to change anything because there won't be any much difference between this point and that point, right? I'm essentially talking about two points, like one of them is in here and the other one is in here. So it looks like if you just draw a perpendicular line from that point to the symmetry axis, somehow you reach to that point in here. But since this point is too far away from the capacitor, it actually shouldn't be affected by this fact, actually, right? And somehow we see that this property also holds true for nearby points as well. So the magnetic field in here is exactly equal to the magnetic field in here. Right, there are some approximations in here. One of the approximations is this, the parallel plate, infinite plate assumption, right? We have assumed this to actually claim that the electric field between the plates is uniform and it is zero outside and things like that. In reality, we know that this is not true. In reality, there are these, what we call is like banding of the electric field lines in here. And outside there are some fringe fields, right? So because of that, this is not really exactly equal to the magnetic field in here. There are small differences, but usually if this is like a capacitor where we can make this approximation, the difference is very small, right? Okay, so in any case, so this is the only problem that I can solve from this topic, right? From Maxwell's correction to the Ampere's law. But I'm going to ask a question like that in the exam, right? I will definitely ask a question like this. So I asked the magnetic version of this. In that case, there was a magnetic field between some cylindrical region, and then I asked for the value of the electric field inside or outside. This is just the analog of that problem, but the fields just replaced each other, right? Okay, so let me stop here. In the second hour, I'm going to talk about the implications of Maxwell's correction. Yeah, there are many things that we need to talk about. One of them is the electromagnetic wave, so I'm going to talk about this. But I'm not going to go into the calculations. I'm just going to describe this qualitatively only, but in the past year's videos, there are these discussion of the some of the integrals and things like that. So I also did use some of the formulas. The other thing is, I think I need to talk about these magnetic monopole thing. I think this is an appropriate point. And then perhaps I can talk about a little bit about this quantum mechanics, actually. Okay, so let's leave it in here. Let's meet back at 9:40.